Shota with the presentation titled The Place Where Origami and Differential Equations Meet. You have your audio is recorded.
I think yes.
All right. Well, take it away.
Thank you. Thank you. So, hello, my name is Shota Shigetomi. Thank you for inviting me today. I would be happy if you would speak English a bit slower so that I can understand easily. Thank you. So today's my talk's title is The Place Where Origami and Differential Equations Meet. 折り紙と微分方程式が出会う場所。So I'm gonna talk about mathematics behind Kaleidocycles. So I'm very sorry I forgot to bring Kaleidocycles, but here you can see images of Kaleidocycle, and basically like Kaleidocycle has interesting because it has like inverting motion like this, looks like bubbling, and this deformation can be regarded as a deformation of discrete curve like that. And basically today I'm going to talk about the deformation of that kind of deformation of discrete curve. Okay. So first of all, let me introduce myself. I am So my name is again Shota Shigetomi, and I am working as a postdoc researcher at Kyushu University. My hobbies and interests like taking photographs and enjoying art, traveling, and math. Like there are three photos I took. I think this is like I think art gallery of South Australia. Yeah. It's free to enter, free to take photos. It's great museum. I really like it. And that one, I think it's Gardens by the Bay in Singapore. It was like really nice place to visit. But it's like temperature was like too high. Around I think 40 degrees. Like it's my I'm not used to that kind of high temperature, so it was also hard time for me. So okay, and that one is famous opera house in Sydney. Yeah. Okay, let's talk about math. Why am I interested in mathematics? Basically, actually, I was originally interested in space and physics, not just mathematics. So I majored Earth and planetary sciences at the university. Like I went to Hawaii to study about the volcano. But I didn't continue that study.
Was it too hot there too?
Yeah, actually, very, very hot. I can't stay that much. So for my thesis, I worked on the equation, nonlinear differential equation called the Friedmann equation, which is an equation that appears in cosmology. Some of you might know about differential equations, but some of you might not. Okay, so let me explain about differential equations here. So differential equations are equations that focus on infinitesimal changes in the function. Here is one example. So dot means that the derivative with respect to t time variable, I mean, then you can check that this one is a solution to this equation. So as you can see, how should I say, you get functions as solutions to differential equations. I mean, yeah, we have quadratic equations as a conversion. So maybe you're familiar with this kind of equations, and basically this kind of equation as a solution to this kind of equations, you get number, not function. Okay, so that's I think the biggest difference between differential equation and algebraic equations like this. So, okay, in general, solving differential equations is very, very difficult. This is like, I think one of the most simple example of differential equation. It's very easy to solve. But basically, differential equations appear around us is like called nonlinear equations. It's very, very difficult to solve. Even computers can't solve it easily. In particular, so as I said, in particular, finding exact solution means that this kind of, how should I say, function that satisfies the differential equation. I mean, how should I say? So you can solve differential equations numerically by using computers, but it's not exact solution. Okay, it always includes some small error. So yeah, finding exact solution is important. Okay, but in particular, finding exact solutions to nonlinear differential equations is extremely difficult. Okay, the Friedman equation, which I studied when I was undergrad, was nonlinear, but could be solved exactly. So I felt like why this equation can be solved, and then that interest led me to change my major to mathematics. So how are physics and mathematics connected? Most of the physical phenomena around us are written in terms of differential equations, like motion of objects, flow of liquids, currents through circuits. All of them can be described in terms of differential equations. However, as I said, finding exact solutions to differential equations is very difficult. But there are some special equations that can be solved exactly. So systems of nonlinear differential equations that can be miraculously solved are called integrable systems. Here are some well-known equations. So this is a Kaleidocycle equation. We call it KdV equation for short. This is a modified KdV equation. This is Sine-Gordon equation. KdV equation and MKdV equation are known as the equation of wave, and the Sine-Gordon equation is known as the equation that generates a certain surface. So this equation related to geometry, and these two related to physics. Also, this can be regarded as a, how should I say, equation for a pendulum. Yeah. So yeah, all of them, in that sense, all of them are connected to physics. And okay, so integrable systems appear in many fields, including physics. They are closely related to waves called solitons. Here you see some example of soliton waves. So these three animations animation of the solution of the KDB equation. So this one is one soliton solution. This one is a two soliton solution, and you can see that the what waves moves without collapsing, and that one is not soliton solutions, but periodic wave. But this kind of periodic wave can be thought of as an infinite number of solitons, and soliton solutions are obtained as the limit of that kind of periodic wave solutions. Okay, and also it is known that integratable systems can be discretized, preserving the structure of the solution, and that is why we talk about we need to use integratable systems to how should I say, to research Kaleidocycle, because it's obviously discrete object. Okay. It is also known that the solutions to integratable systems can be written in terms of the theta functions, exponential functions, like that. Soliton solutions are written by using exponential functions. Periodic solutions are written in terms of theta function. So what is theta functions? My research deals with the elliptic theta function among the theta functions. They are defined as follows. So theta functions are important function in various areas of mathematics and physics, like not only integratable systems but also like number theory. You can you can use theta functions to research. Okay, so so theta functions have many good rich mathematical properties, and basically in my research the most important property for me is like identities of theta functions. Okay. Theta functions have a number of remarkable, as I said, that's okay. And so what is identity? Okay. So identity is like equality where the equal sign holds for any number. So here we have example. This equal always hold for any x, right? So if you substitute x is equal to 0, then you get 1 squared is equal to 0 squared plus 2 times 0 plus 1 is equal to 1. So equality holds, right? As a comparison, we have equality that is not identity, this one. So obviously that equal sign holds only when x is equal to -1. Okay, that's the difference. Okay, and basically the identities of the theta functions can be used to solve integratable differential difference equations. So these are just examples. This kind of identities is very important. Okay. Okay, so now let me introduce differential geometry and discrete differential geometry. So differential geometry is the study of geometry using the techniques of calculus. The shape of a curve, that kind of smooth curves, is determined by the curvature and torsion. The curvature is like a quantity that indicates how much the curve is bent. Torsion is a quantity that indicates how much the curve is twist it. Okay, so the torsion, if the curve's torsion is 0, then it's like a completely planar curve because it does not twist it at all. Okay, so and discrete differential geometry is a kind of discrete analog of differential geometry. This is useful for industry, for example, when processing shapes on the computer and when machining parts. Sometimes discrete versions can be mathematically richer, so that's another reason why discrete differential geometry is important. When discretizing differential geometry, concepts and methods of discrete integrable systems are often used. In this connection, theta functions appear when constructing curves and surfaces. So these two curves are maybe exactly the same, but maybe I'm not exactly the same, but maybe discretized version of the curve above. And yeah, so all of the four curves are expressed in terms of theta functions. Yeah. So here I'm gonna explain a bit more about discrete curves. Basically, discrete curves are like shapes consisting of polygonal lines like that. And here you see an illustration of a discrete curve. We name it gamma, and the shape of a discrete curve can be determined by examining the three vectors tangent t, normal n, and the binormal b. From these three vectors, we can calculate curvature, discrete version of curvature and discrete version of torsion, which are particularly important when determining the shape of the curve. So kappa is angle, basically angle between adjacent tangents, and this indicates how much the curve is bent. And lambda is an angle between adjacent binormals, and this indicates how much the curve is twisted. So now let me introduce Kaleidocycle. This is a closed linkage mechanism that is composed of identical tetrahedra joined by hinges. It has many interesting properties. For example, it has like everting motion like that, can be made with origami, and many more properties. But because we don't have, I think we don't have time to explain that. So okay. There's an interesting known result about formulation of Kaleidocycle. It is modeled by considering deformation of closed discrete curves with constant torsion angle. The motion is expressed by integrable equations. As a next step of the research, constructing an explicit formula of Kaleidocycle is important. If we have an explicit formula means that maybe explicit solution. It will be great help to find more properties of Kaleidocycle. So in my research, I constructed an explicit formula for Kaleidocycles. So the math about a math behind Kaleidocycles. Here, there are like two math areas are important in my study. One is discrete differential geometry. This is a study of geometry of discrete curves. Why it's important? Because the deformation of Kaleidocycles can be regarded as a deformation of discrete curves. Another one is integrable systems. This is a study of systems of exactly solvable nonlinear differential difference equations it is known that discretization, preserving the structure of solutions, is possible for integrable systems. It is helpful for constructing the discrete version of differential geometry. So why it's important? Because integrable equations arise as a deformation equation of a Kaleidocycle. Also, when constructing explicit formulas, integrability is important. Okay. So let's look a little closer at how Kaleidocycle and discrete curves correspond. The part of the Kaleidocycle shown in the image on the left, circled in red, is illustrated in the middle figure. So this red line represents the hinge, and I'm sorry, so maybe I have 3 former slides. Okay. I will be. Maybe I skip this slide. Okay, so the middle point of the hinge is how should I say, the position vector of a discrete curve. Then you get this blue line by connecting the gammas, and then you get this discrete curve. So that discrete curve has constant torsion. So the torsion does not depend on n nor t, because this is constructed by same tetrahedrons, and this is the main result. Putting these 3 functions f, g, h, and then you get this gamma is a discrete space curve with constant torsion angle and segment length. When the parameters r, v, and y satisfy this condition, the curve is closed, and you get that kind of blue discrete curves. And also curvature and torsion are explicitly written like that. That is the most important part, but I don't have time to explain it. From the explicit formula, we see that the deformation equation, the gamma satisfies this deformation equation, and from this equation we get this equation for curvature angle. So this is a discrete version of MKDV equation. So this is integrable equation. And the summary. And in my research, an explicit formula of Kaleidocycle obtained. Deformation equation is this, and also this is famous in discrete differential geometry, I think. And also as a equation for curvature, we get this equation. This equation is, I think, also famous for as a discrete version of modified KDV equation. This can be, これ言ったので OK. So thank you for listening. That's all.
Thank you very much. We have some time for some questions. I have a lot. That is possible. But floor is open for questions. Go ahead.
I have a question.
Yes.
So, which came first? Some creative origamiist created the Kaleidocycle, not knowing any math or anything. And then a mathematician came behind and described it using all of these equations, or is it the reverse?
I think someone, I'm not sure the history of Kaleidocycle, but I think someone created first as a kind of hobby, not mathematics, I think.
It's amazing that it can work that way.
Yeah, just like, oh, look what I did. Okay, let's study that. Yeah, exactly.
どうぞ。
この、折り紙の動きを多分理算的に計算して、再現したっていうことだと認識しています。
というよりは、まあこの折り紙がまず厳密にこの離散曲線として、ある一定の条件を与えないといけないんですけれど、とにかく離散曲線としての変形としてこうモデル化できると。要するにその解くべき方程式だけは見つかっていてっていうのが、先の最初の方に出てきた、リサーチなんですけれど、どこ行ったかな。ここかな。ここへちょっとちらっと述べたこの梶原パクの研究なんですけれど、でその方程式は分かったけれども解かれていなかったっていう、でそれを厳密に解きましたっていう。はい。はい。
普段上理論方程式が結構触るので、その解く難しさっていうか、きれいに解けることってそんなないと思う。
そうですね。あまり解けないですね。
すごいなと思ったという。
ありがとうございます。僕微分方程式を解くのが大好きで、本当ですか。なるほど。確かに数学会とかで喋ってても結構その感覚で解くんですよ。僕はこういう解をどうやって見つけたんですかってそう聞かれ感覚ですってそうですかっていうはい。そうですね。はい。
それはそれも感覚ですか。
だからそうですね。なんか最初にこれがいろいろな方程式がたくさんあって、その方程式の下でこのカーブがそのカライドサイクルに対応しているっていうのが分かって、でそのたくさんの方程式を眺めつつ、そのたくさんの方程式とこういう高等式をね見比べてどういうふうにすればいいかなっていうのをこう感覚的にそうなんですよ。だからなかなか数学の偉い理論を使ってその説明するっていうのがちょっと僕は逆に苦手というか、数学科じゃなかったから学部がでそこが抜けてて、そうありがとうございます。
Probably one technical question. This is for just a general. We've talked a lot about your work today. How has, say, like the field of mathematics, or like even like you're working, how has that changed with the development of, say, of like technology and new theories coming out? Like, has it gotten easier? Is it the same? Has it gotten harder? Mathematics seems like the purest form of science and research, but like, does technology even like help with that, or is it like what you said? You look at this, you look at the other forms, and kind of like you gotta work it in your head. It's like, there we go.
Well, like computers help us a lot, and then mathematicians basically compute something that cannot be computed by like machines. Yeah. So as technology involves the goal, the thing we have to calculate is like also evolves, also changes. So in that sense, yeah, technology helps a lot, I think. Is that a right answer? I'm not sure.
It's a fun answer. I think it's it's an unfamiliar territory. It's fun to get a perspective on. Okay, I think that's half an hour. Shota, you'll be staying around if people have questions or more so. So please ask him any additional questions. But yeah, thank you very much. Give him another round of applause.